So today I'll be talking about making jet fuel out of the sun and the wind, and whether that's something that it makes sense for us to pursue. Again, I'm a postdoctoral research fellow at Stanford University, and I have my PhD in engineering and public policy from Carnegie Mellon, as well as a master's degree in machine learning.
And Evan, if I could interrupt you just for a moment. Everybody's welcome to put in questions on the chat window while Evan is talking. Krista's put out a chat already inviting you, but please check that out. And then at the end, you can unmute yourselves and we'll have a kind of live Q&A session. But feel free to put in, immediate questions or comments during the chat while Evan is speaking. Sorry, go ahead.
Definitely, thank you. So a bit more broadly about who I am as a researcher. My research focuses on the role of hydrocarbon fuels in a net zero emission future. So this is, broadly speaking, energy and climate decision focused research, and sort of four major areas, one of which I'll talk about in detail today. I'll give some tastes of the others. Methane leakage, methane emissions from the natural gas value chain is a major area I'm working on right now, particularly remote sensing, airplane and satellite-based methods for finding methane emissions. I'll talk a bit about at the end. Energy systems modeling, which is what I'll be talking about today. Machine learning and energy consumption behavior analysis. So today I'll be focusing again on energy systems modeling, particularly what's called techno-economic analysis, trying to figure out how much something that we can't build yet is likely to cost or haven't built yet, and systems dynamics modeling and optimization, so modeling a system in motion. And the big motivating question behind this research is, can we keep our $200 billion worth of airplanes or $125 billion worth of heavy trucks or $50 billion worth of ocean ships, and this is just those registered in the United States, a significant amount of capital that we have. It would be great if we could keep using it in a net zero emission future, especially given that globally, this represents about 6% of fossil fuel and industry-related carbon dioxide emissions. So in addition to this broad question, I've also got a sort of more researchy question of, can we use, or how can we use, optimization to guide research development and deployment priorities for emerging technologies? And a bit more detail on this: renewable electricity is getting super cheap, but it's variable. The sun, is available some of the time, same with the wind. And that's going to make it difficult to use renewable electricity to power capital-intensive processes where you have to build a bunch of stuff that's expensive to build, and you kind of want to use it a lot of the time if you can. And optimization lets us explore these trade-offs of designing and operating large or capital-intensive systems that are designed to use renewable electricity as efficiently as possible to produce chemicals or something else along those lines, and really understand how the dynamics of that system change as the technology advances. And this helps us identify what might be non-obvious priorities for research, development, and deployment. Where do we invest in a given component? Do we want to make this component a little cheaper or more efficient or able to turn on and off faster? These are things that we can evaluate using this type of model and guide where we put our money to improve a given suite of technologies. And this work I'll be presenting today was published just last month in Environmental Science and Technology. I'll include a link to the paper. We can put it in the chat or something along those lines. If you would like more detail on this work, please feel free to check out the paper. So there's a real push, as Max alluded to, in the attempts to decarbonize the energy system, to electrify pretty much everything we can. It makes a lot of sense. Renewable electricity is super cheap, and it's basically zero carbon. So if we can just build a lot of renewable electricity and make everything run on electricity, then we've kind of solved the problem. And some of the economic motivations for this, natural gas electricity is somewhere in the ballpark of $50 per megawatt hour of electricity produced. And wind and solar at the best locations, at least as of a couple of years ago, about $40 a megawatt hour. So in terms of bulk energy, if it's okay that the energy comes at whatever time it comes, wind and solar in the best locations are already the cheapest form of energy or electricity that there is. And in some places, it's way cheaper. In Mexico, even a few years ago, we were seeing power purchasing agreements coming in around $20 a megawatt hour. So that's half what these United States numbers. And we're hearing numbers closing in on $10 a megawatt hour in places like Saudi Arabia. And even if that's underbidding somewhat, that's still an indication that these costs are really coming down. So wouldn't it be great if we could run airplanes on electricity? Batteries are not there, probably never going to get there for long distance flights, but with electrofuels, with carbon neutral hydrocarbons, we can do that. And how can we do that? I'm going to start with the cartoon and then go into a little more detail in a minute. Electrofuels start with electricity, and you mix that electricity together with water and do electrolysis of water, which splits it into hydrogen and oxygen, which I didn't picture here. Then you take that hydrogen and you mix it together with carbon dioxide that you've somehow taken out of the atmosphere. I'll get to how one might do that in a minute. Well, then you've got carbon, you've got hydrogen, so you can make hydrocarbons. That's the basic idea. Of course, there are a lot of steps in between there, but with a hydrocarbon like this, once you burn it, yes, it emits carbon dioxide, but that carbon dioxide is just going back into the atmosphere where it came from in the first place. So assuming the process of making electrofuels doesn't emit emissions, it's net zero. In this analysis, I'm focusing on jet fuel. And the main reason for that is, one, aviation is a super difficult application to decarbonize other ways. There's talk about hydrogen airplanes, or for short haul flights. Electrification could work, but we're probably not, given how long it takes to approve new airplane designs and the state of the technology at present, we're probably not going to see hydrogen airplanes coming online in a big way for a couple decades at soonest. So if we want to keep using airplanes and want to get to net zero emissions, we basically need a net zero emission liquid fuel. And the good news is that electrofuels are already approved for commercial blending, blending it up to 50% into commercial flights. And that number could go higher if we add some additives. So this is something we could do today. This is not a far-fetched technology. So the more precise question that this talk's focusing on is, under what circumstances are electrofuels cost effective for decarbonizing aviation? Under what circumstances is this something we would want to do? And secondary question is, what should our research, development, and deployment priorities be if we want to get there? All right, so getting into a bit more detail, the system that I'm looking at here is producing electrofuels using direct air capture as the carbon dioxide source. So I'll walk through the process. You start with electricity from the sun, from the wind, and I should note that Max helped design this figure. And that electricity is used for a few things, one of which is to power a direct air carbon dioxide capture system. And direct air capture there are a few different designs, but fundamentally they're all basically a big cooling tower on its side, usually, that is blowing a bunch of air across some large amount of surface area, usually with a fan or something like that. And on that surface area, there is what's called a sorbent. And that sorbent, it's some kind of chemical, binds to carbon dioxide in the air. And then that sorbent is regenerated by, you basically throw a bunch of heat at the sorbent, and it releases the carbon dioxide and regenerates the chemical, which you can then recycle. And so you get this pure stream of carbon dioxide coming out on one end. And by putting in a bunch of energy, you are able to continue the process. And the heat requirements here, so there are two basic types of direct air capture, at least two basic types that are commercially available or under advanced stages of development. There is a relatively low temperature system called, such as that produced by a company called Climeworks. That requires about 100 degrees Celsius heat, so about boiling, in order to regenerate the sorbent it uses. And then there's a higher temperature system, such as that produced by Carbon Engineering, which is requires heat at about 900 degrees Celsius, so significantly hotter. That also requires a bigger facility, but there could be some real advantages to that approach as well. For the heat source, I'm assuming one heat source, if we want to run this all on electricity, could be an electric kiln. We're really good at electric resistive heating. We've known for a really long time that if you run electricity through a resistor, through some metal with that's going to dissipate heat. And we can get up to the temperatures that we need. There are furnaces available that do this right now with basically close to 100% efficiency. So that's an option. It's also going to take some water for the high temperature systems. Low temperature actually produces a bit of water. And out of that, you get carbon dioxide. So then we've got our electrolyzer, also powered by electricity. And that's going to take in some water as well and produce hydrogen and oxygen, which I didn't include on the graph, but is important for other parts of the system that I won't get into today. And then you run it through a fuel synthesis system. And the fuel synthesis, I'm assuming, is what's called the Fischer-Tropsch process, preceded by what's called the reverse water gas shift process. So reverse water gas shift takes carbon dioxide and hydrogen, mixes them together, and produces carbon monoxide and hydrogen. Once you've got carbon monoxide and hydrogen, you can then run that through. So this Fischer-Tropsch process was developed in, I think, the 20s to take a gasified anything. It could be gasified coal or biomass and turn it into liquid fuel. So once it's got, you can get your carbon monoxide and hydrogen from anywhere. Once you've got that, you can make liquid fuel with basically the same rough product distribution as refining oil. So potentially as high as I've seen up to 60% jet fuel, and then some diesel, potentially some gasoline or precursors to gasoline, which are not that difficult to upgrade. So we could get a decent amount of jet fuel out of this, this approach, and there would of course be markets for the other products as well, which would also be net zero emissions. So the result's hydrocarbon fuel. And to give a sense of the energy requirements here, if we want to produce a barrel of oil equivalent of electrofuel, that's about 1,600 kilowatt hours. The direct air capture would require about 600 to 1,100 kilowatt hours of heat, somewhere between 35 and 340 kilowatt hours of electricity. And the high temperature system would take about 2.3 tons of water. The low temperature system actually produces half a ton. The electrolyzer is really the big ticket item as far as energy is concerned. This is taking in almost 3,900 kilowatt hours of electricity to produce less than half of that in terms of electrofuel. And it takes in about half a ton of water. So, of course, the energetics here are not, on a pure energy basis, favorable at all. But remember, renewable electricity is super cheap, especially if you build it in the right place. So what we're doing isn't turning one kind of energy into the same kind of energy, just less of it. We're turning a kind of energy we can't use for things like aviation or heavy shipping and turning it into something that we can, which is potentially quite valuable. But for those watching, many probably can see here, well, wait a second, this is using some pretty capital intensive equipment. We've got to build this whole big direct air capture system, the fuel synthesis, to a lesser extent, the electrolyzer. We probably want to operate these pieces of equipment more often than just when the sun's shining, when the wind is blowing. So it'd be nice to have storage of electricity, lithium-ion batteries, heat storage, which could be molten salts or supercritical carbon dioxide, or even phase change materials, which can get essentially to the heat requirements for high temperature direct air capture, and hydrogen storage, either a big tank or if you're close to a salt cavern, something like that. Carbon dioxide storage, pressurized in a tank. You might even want to build a fuel storage system, just a big tank like a gas tank, and build a smaller pipeline, something like that. So those are some forms of flexibility that the system can use to help run, say, the direct air capture more of the time than the sun is available, or the wind. But wait a second, if we're already in a world where we're pulling carbon dioxide out of the air, then there's really no reason we can't supplement this system with a natural gas interconnection and offset the resulting carbon dioxide emissions from the natural gas by paying somebody else at a different facility to capture the equivalent amount of carbon dioxide out of the air and put it in the ground, sequester it. So it's still net zero as long as that takes place. And this could provide some really important flexibility to the system that reduces overall costs while remaining net zero. And the same is true for grid electricity, which for the next, for a while is going to have some emissions associated with it. So I'm going to revisit this, sometimes this question of net zero fossil energy interconnections requires a little extra explanation. So I'm going to have a slide on this. The model basically uses a carbon price to penalize the use of fossil energy. And that carbon price is the cost of, it's paying some other facility somewhere else to do direct air capture with sequestration to offset the equivalent amount of carbon dioxide to anything that's emitted from or produced from combustion of natural gas or from grid electricity. And I should note that the natural gas we're assuming is oxygen, I'm assuming is oxygen fired in the direct air capture system. So it's actually co-captured with the rest of the waste stream and then can be put into the electrofuel. And since it's offset by direct air capture at another facility, again, still net zero. And yeah, so the cost of offsite direct air capture is just commensurate with whatever the scenario I'm assuming assumes that the cost of direct air capture is. So for those in the energy modeling world, looking at this problem, we've got variable renewable electricity. We've got all these capital intensive assets. We have to decide how much of each one to build. How do we operate them throughout an entire year? This is an optimization problem. And that's exactly the way I structured it. So it's a linear optimization, nothing super fancy in terms of the model formulation. And what we're minimizing? We're minimizing the annualized capital and fixed operations and maintenance costs plus variable costs. Essentially, we're minimizing the cost of producing the fuel. That makes sense. And I've constrained the model to produce a certain amount of fuel per year. 7.5 terawatt hours of liquid fuel, or about 4.5 terawatt hours, about 7.5 barrels per day of oil equivalent. And the reason I did that was to make sure that the model reached full economies of scale for all system components. And in this case, the direct air capture system is the main one that I wanted to make sure was being built large enough. So this is pretty big by renewable electricity installation standards if we're building a big solar array or wind farm to power this, but it's tiny by oil refinery standards. And that's a reminder of how energy dense hydrocarbon fuels are. So some other constraints, the renewable electricity production, when the sun's available, when the wind's available, the model can't vary that, that's fixed. Makes sense. The production and storage in a given component. We can't have a production level that's higher than the capacity that's been built for the component. Same with storage. These are all kind of common sense constraints. And the real heart of the model is conservation of energy and matter, because things like electricity or hydrogen could go in a few different places at a given point in time. And the model keeps track, does the accounting of where everything's going, accounting for losses and stuff like that. using conservation of energy and matter. And then there are also constraints on how quickly some of the components can turn on and off, ramping constraints. And I built this model in the Analytica optimizer with the Gurobi solver. So a bit more about the structure of the model. I'm just going to show some of the, show all of the decision variables. So this is, again, an optimization-based techno-economic analysis with 13 capacity decisions. So we've got on the left-hand side the total capacity for renewable electricity generation, the electric kiln, the electrolyzer, direct air capture, fuel synthesis, and then the interconnections to the electric and gas grid if the model decides to build those. And then on the right-hand side, we've got the capacity for all the different types of storage, as well as the fuel pipeline that ships all the fuel out to market. And so those are 13 capacity decisions. But then we've also got, if we do 4-hour resolution, which is what I did for this paper, over 1 year, that's almost 66,000 operational decisions. So we've got the production profile, at what level of production is each of these components over time? And of course, the renewable electricity, that's fixed. Ramping, how rapidly are these components turning on and off? There's some constraints there. There's some energy consumption associated with some of those components turning on and off or ramping up and down. And waste, so curtailment, particularly for renewable electricity. At some times, it might not be economical to build, all the capacity so big that it can use all the electricity that's available at the peak hour of the day. It makes sense at sometimes to discard some of the excess energy, mostly in terms of electricity, some heat. It doesn't really throw away anything else. And then for storage, we've got, of course, our inputs, our outputs, or our levels and our outputs for each of those components in each time step. And this model is available, freely available online. I call it the Power to X optimization tool, PTX-opt. And I'll show the full optimization formulation in a second. And I can include this, this link's available in the paper. I can stick it in the chat if that would be useful. And I'd like to take a minute at this point to talk a bit. This is an Analytica webinar. I used Analytica for this model, and I'd like to talk a bit about what I see as some of the real advantages of Analytica for this type of modeling. I began this modeling effort with not that much time left in my PhD. Time was of the essence, and if I thought it would be faster and more effective for me to write up this code in Python or R or MATLAB or some other language, all of which I know and use for different things, I would have done it. But I chose Analytica. And there are a couple of real advantages here. Probably the biggest one for this type of modeling is the ability to make structural changes in the model with pretty little additional effort pretty late in the game. So some other advantages as well, the visual layout, for those who haven't used Analytica, it's designed, it's not a screen full of code, it's a bunch of different nodes that relate to each other, and you can see what relates to the other nodes. And the notation is also very compact, and it's so instead of having like a giant for loop or hopefully not too many of these, but a big array of spreadsheet sheets or spreadsheet cells, and then another one with an operation done, all those. It's very compact notation. So, but again, I think the biggest thing here was for rapid agile model development, the ability to make large structural changes to the model pretty at basically any point in the development process. So again, I call it this model the Power to X optimization tool, PTX-opt. And I'm not going to go into detail of exactly everything I'm about to show, but this is the full optimization formulation of the entire model. And the main thing I want to point out here is that this whole thing fits on one page. It's not that complicated a model. Of course, it's complicated by more complicated than a super simple model, but it's got a simplicity to it. So, well, now one of the hardest or most time-consuming parts of this process was figuring out all the parameters that I wanted to put in the model. And one of the most important ones is, where do we build this system? Where are we assuming that it's coming from? If we can build a system kind of wherever we want, we're not really geographically limited. Why not build where the best sun is? So in the United States, that's somewhere like Tucson, Arizona, 29% capacity factor. And that means that a solar installation there with one-axis tracking would produce 29% over a year as much electricity as if the sun was just overhead at like high noon for an entire year. So that's, as solar goes, that's about as good as it gets. And I'm using data for the entire year from the National Renewable Energy Laboratory's System Advisor model. And for wind, I did the same. This one's probably a little less scalable, but the best wind resources in the US are somewhere like southern Wyoming, has a 58% capacity factor. So the wind is blowing flat out an awful lot of the year. And the result of picking these really good locations for wind and solar electricity is electricity costs that are today, and the today case, I use three main cases: today, next decade, and by 2050. And the today case is based on the peer-reviewed literature and government reports. So it's necessarily somewhat conservative because there's a couple-year lag. So, but today I'm looking at about $40 per megawatt hour of electricity. In the next decade case, falling to $20, $30 per megawatt hour, depending on the technology, and into the teens by 2050. And happy to talk in more detail about how I got each of these numbers. And there's a lot to go into that I won't be able to in the span of just one talk, but it's all on the paper. And for direct air capture, this is the other sort of major parameter, which doubles as the carbon price. For high temperature and low temperature systems, well, today only low temperature systems are, at least as of when I wrote this, commercially available. There is a high temperature system under construction at scale right now. We don't know, what exactly the costs are coming in at, but it's a promising development. So $600 a ton for low temperature systems today is based on kind of whispers of what early stage projects cost. And for costs almost always come down quite a lot from the first few of a kind to once you get to larger scales. So I anticipate that.
Sorry to interrupt, Evan. The units for the direct air capture, is that dollars per ton per year?
This is levelized costs. So this is dollars per ton of carbon dioxide removed.
Okay, over the whole lifetime of the thing.
Yes.
Okay.
And so that's assuming that this is operating at 90% capacity factor and sort of a dedicated plant.
Good.
Could I ask also about the top one?
Sure.
Is that the cost of, I'm just kind of unclear what I'm saying. Is that the cost of electricity that's being used by the system? Because we're not producing electricity, we're producing jet fuel. So I'm just confused what the price is.
Yes, this is the cost of electricity that's being used by the system.
Okay, got it.
Great. And again, these so direct air capture costs in the next decade, and I'm being these numbers are probably somewhat conservative, at least from the standpoint of the direct air capture industry. Some of these companies think that they're going to be at $200 a ton well before the end of the decade, and some perhaps even at $100 or so a ton by 2030. So it's possible, and I hope that that's the case. But these are the assumptions I made for this model, and again, these numbers double as a carbon price. And here are some of the key assumptions in terms of the capital cost of each individual component. I'm not going to go into detail on each one, but if anybody sees a number and wants to ask about it in the Q&A, I thought I'd at least flash this up. And of course, we can go back to this in the Q&A, and everything's in the paper. So here we are. How much does it cost to make electrofuels under these different sets of assumptions? On the y-axis here, we have the levelized cost of electrofuels, basically the pre-tax cost of producing electrofuel. In dollars per liter of gasoline equivalent. So going up to 5 here, which is a hint of where it's gone. And then on the x-axis, we have these different scenarios. So the today case, next decade, and by 2050 for both high temperature and low temperature systems, although I didn't model high temperature today. And I'm about to show some stacked bar charts that show the different, how the different components contribute to the total cost of electrofuels. And if we were to build, oops, I went backwards. If we were to build electrofuels, solar electrofuels today, using the assumptions I put together, we're talking about more than $4.50 per liter of gasoline equivalent. Multiply that by about 4 to get dollars per gallon. So this would be pretty expensive. But again, very early stage, costs generally come down quite a lot as development moves forward, deployment moves forward. And the big cost contributors are renewable electricity generation. So this is the solar panels in this case, the capital and the operations and maintenance costs there, the electrolyzer, and the direct air capture system. And that fourth big black bar at the top, again, remember that those net zero natural gas and grid electricity interconnections, that is, the model decides in this today case that it's so expensive to produce direct air capture in particular, but electrofuels in general, that it actually makes sense to use a fair amount of natural gas and grid electricity to keep the whole system, or as much of it as possible, running at a very high level of utilization, even though that means paying $600 a ton to offset that resulting carbon dioxide. That starts to change if we get to this next decade case, where costs fall quite substantially to about $1.70 or so per liter of gasoline equivalent. The major cost contributors are the same, sort of the biggest components are pretty much the same. But this is now in the range of a lot of biofuels, especially biofuels that are compatible with for jet fuel substitutes. And note that the cost for high temperature or low temperature direct air capture systems is basically the same for the two different electrofuel production systems, which is I think an interesting result, because the one's more capital intensive, one's more energy intensive. And if we get to this by 2050 case, if we're able to achieve these numbers, then we're down to about $1 per liter of gasoline equivalent. So that is pretty close to the price of jet fuel. The pre-tax price of jet fuel here is, you can see the dashed line is the average over the last 10 years in the United States. And then the dotted lines are the 1 year average high and the 1 year average low over that same period. So it's not quite there to the high over the last 10 years, but it's pretty close. And then if we account for the fact that if we're heading toward a net zero emission world, we'd be willing to pay a certain amount to extra to offset those emissions, then this is looking potentially quite good. And for wind, it's pretty much the same story. So it looks like today we wouldn't want to do this on a super large scale, but at the same time, in the long run, there are very real prospects that this could be potentially our least cost option for getting to net zero while maintaining aviation and some of these other liquid fuel dependent applications. And well, this raises the question: if we're here today and we want to get to here, what should we focus on if we want to bring those costs down? So here we have the a sensitivity analysis I'm about to show. On the y-axis is again the levelized cost of electrofuel, dollars per liter of gasoline equivalent. And note that the y-axis does not go down to zero. And on the x-axis, we've got the percent change in inputs. So we're starting from the solar next decade high temperature case. So this again, a next decade case in that middle case. And I vary each input from its today case, so the more conservative value, to its by 2050 case, the more optimistic value. And under those, and the result is some percent change in the inputs, which is what's reflected on the x-axis, and that translates to a change in the levelized cost on the y-axis. So let's start with direct air capture. which is the most sensitive parameter, the capital cost and fixed operations and maintenance costs of direct air capture, which introduces from bottom to top, a swing of, what's that? More than 60 cents per liter of gasoline equivalent. So that's a priority. That has to come down if we're going to get to lower costs for electrofuels. And then I'm going to show actually not all the other parameters, but everything else with a swing of more than 10 cents per liter of gasoline equivalent. And one thing really jumps out, which is that the top three most sensitive parameters are all the capital cost of those three big cost components, which that makes a lot of sense. No surprises there. Fuel synthesis capital cost is kind of it's there, but it's not as sensitive. And the weighted average cost of capital and lifetime of the equipment, those are just numbers that we use to convert capital cost into something that's comparable with, say, energy purchases or something like that, something that we use in a given year. So really the six most sensitive parameters here all relate to capital cost. But following on that, we actually get to a somewhat different story. So reducing capital cost is key. That's no question about that. But flexibility is also, these are the two most important parameters, fuel synthesis minimum production and the hourly ramping rate, how quickly it can turn on and off. Those are the two most important parameters after those first capital cost parameters. And so the difference here is, in the today case, I'm assuming that the fuel synthesis system just has to operate flat out all the time, which is pretty much how a lot of large-scale chemical processes along these lines work today. But even the ability to just go to 50% production from here to here, or the ability to, or related to that, the ability to ramp down, ramp up and down by 5% per hour. So essentially the ability to turn the plant on and off in a day. So not super.
So Evan, the fuel synthesis maxi hourly ramp, it's horizontal on the right side, but then it ramps up on the left of the
exactly.
ramp.
Yeah, so
that means, well, higher ramp rate we don't care about, lower ramp rate has an effect.
Exactly. So really all we need to get to is the ability to turn one of these facilities on and off in a day. Getting it on and off in 4 hours doesn't get us that much more. And one thing that I think is kind of remarkable here is that for all those forms of flexibility that have been introduced into this model, the different types of storage, the natural gas and grid electricity interconnections, very little of that actually shows up as sensitive here. And that's not because flexibility isn't important. It's because a lot of these forms of flexibility are substitutable with each other. And to illustrate some of that, and what I mean by flexibility, I'd like to, I'm showing here a chart of average utilization, daily average utilization by component. So starting with the electricity, this is, so again, averaged over the day, because for solar, otherwise it would just be sawtooth, we couldn't read it. It's an average of 29% utilization factor, capacity factor, but it's pretty steady over time. There's a little seasonality, but not a huge amount. But if we were to run the entire system at that 29%, the cost would go up by about 70%. So, okay, so we need some flexibility to be able to operate some components at a higher level of utilization. And this is the direct air capture. The direct air capture is operating at about 90% utilization. So the system is able to shift energy around and make use of these net zero energy interconnections to make sure the direct air capture is continuing to run at basically full out for essentially all the year. The electrolyzer, it's kind of in the middle. It's more capital intensive than the renewable electricity. So, but it's not capital intensive enough that it makes sense to build a bunch of batteries or something like that to keep it running all day. So it's operating at like 45 or so % utilization, whereas the electricity is only about 30. And that's because it's undersized somewhat relative to the electricity. And in those peak hours, that electricity gets shifted elsewhere into things such as the electric heat generator, the electric resistive kiln, which is super cheap compared to everything else in terms of capital. So it can just kind of soak up a bunch of that extra heat, which is not that expensive to store. And then we've got the fuel synthesis, which keeps on operating about as the direct air capture does, and then the natural gas interconnection, which it ends up using a fair amount to power the direct air capture. So we see that in this case, the various forms of flexibility in the system, storage, and these net zero fossil interconnections, among other things, make it possible for this system to use really expensive pieces of equipment at pretty high levels of utilization and bring the cost down.
So Evan, I assume that the size of each of these components was one of the decision variables.
Yes.
Why didn't the solution basically raise these curves up lower, basically reduce the size of those components so that they were peaking at 100?
Oh, it did. It did. So this is all relative. So this is all just as a % of installed capacity.
Not as a % of the, it says, oh, so the hydrogen, the blue line is hydrogen storage, right?
Blue line is hydrogen production, the electrolyzer.
Hydrogen production, the electrolyzer. So is that saying that the electrolyzer is peaking at 50% utilization? It never gets above 50% utilization?
Correct, because it basically will operate throughout the day. Where the sun goes like this, the electrolyzer goes like this, but it still turns off at night. So it peaks at about 50%.
Oh, so it's 100% at noon, but
oh yeah,
but over the course of the day is 50% utilized.
Exactly. Yeah.
Okay. Oh, okay. Got it.
So this is saying that it's, another alternative would be to have more batteries so that you can keep the hydrolyzer working, 100% day and night. But it turns out that's not cost effective.
Exactly. Yeah. Pretty much the most expensive thing you could do in a system running on variable renewable electricity is to require electricity at a constant value all the time. So we can see that there's
that particular issue, for example, is a function of the relative cost of batteries versus electrolyzers.
Yes. So it's conceivable. If we have some amazing breakthrough in batteries and get it well below $100 a kilowatt hour, we might see a difference in behavior, definitely. So when I talk about flexibility, there are a lot of different types, and we can see that there's some sort of seasonality here. And there's a lot of discussion about seasonal storage in this, the decarbonization community. And I found some seasonal storage. This is in the by 2050 case using solar electrofuels, solar electricity and high temperature direct air capture system. And you can see that, well, whatever this component is, whatever this product is, it's being stored for like 200 days. So the model is shifting something across seasons. And it turns out what it's shifting is carbon dioxide. So it turns out that if the cost of building carbon dioxide storage falls enough, it's about $10,000 today from what I could find. This was actually really difficult to get a good number for. If it falls to about $1,000 per ton, for example, because most carbon dioxide storage is in very space constrained environments. If we're out in the desert, we don't care that much about space. We could probably bring the costs down quite a lot. We actually get seasonal energy storage through carbon dioxide. And I think, and this is something that I don't know if it was on anybody's radar, definitely not on mine before I built this model, but it's something that, again, the model illustrated a potential, something we might want to look into, super low cost storage of carbon dioxide, which I differentiate from sequestration. Sequestration is when you put something in the ground or somewhere and it never comes back. Storage you might want to use later. So this is an example, I would say, of this type of optimization modeling pointing us in a direction for a research and development priority potentially. And another point I wanted to, the last major point I wanted to touch on, again, relates to seasonality in the discussion of electrofuels. So what about the wind? The wind, again, the solar was 29% capacity factor. The wind is operating 58%. It's double, but it's also much more jagged and seasonal. So what does the system do here? This again is averaged over the day for the full year. Wind electricity production is a fraction of installed capacity. It's not as clean a story at all. It's much more difficult to deal with the seasonality, to make the direct air capture keep running at a high level of utilization, the fuel synthesis as well. Those more capital intensive components, the daily variability from solar, super easy to account for that and keep things running at a high level of utilization. With wind, not so much. So in conclusion, I view electrofuels as a tool for hard to reach emissions. This is an approach that would be expensive if we were to do it at a really large scale now, but it looks like it might get close to cost parity with jet fuel. Obviously, the future is very difficult to predict, specifically for energy systems, but it looks like there's a reasonable chance that this could happen. We'd have to bring the capital costs down quite a lot, especially for those three major components: the direct air capture, the electrolyzer, and the renewable electricity. Of course, there's a lot of money going into doing that anyway right now. But we also need flexibility to get this to work. And there are a few different forms. Again, we could just have storage of electricity, hydrogen, heat, carbon dioxide, the ability to turn a given component on and off quickly, or reduce its minimum operating level, or have net zero natural gas or grid electricity interconnections that are offset by carbon dioxide removal. And finally, the ability to curtail excess renewable electricity in particular. And I really view this as both a hopeful analysis for electrofuels and also an indication of this type of tool, techno-economic optimization, as a really useful approach that we can use in a variety of other circumstances to gain insight into potential priorities for research, development, and deployment of emerging technologies. So with that, I'm going to talk a little bit about some of the other things I'm up to, because I'm having a lot of fun and wouldn't want to at least touch on it. So in methane emissions, I am
Evan, I just want to make sure that you leave enough time for Q&A on
okay,
this,
how are we
because
doing?
we have a number of questions that people have come up with. So
very good.
would you rather deal with those first, or?
Okay, so how are we doing on time? I can't see the...
Got another 7 minutes.
Oh, okay, let's go to Q&A. I can make these slides available, I guess, just super quick. I work with a bunch of fantastic grad students. They're doing super cool things. I have a biweekly webinar series, including one today at 12:30 p.m. Email me if you're interested. I work with Climate Change AI and do all sorts of things related to community building there, and acknowledgements for my funders and someone who helped me. And here's my contact information and Q&A.